So good morning all. I am Soubhagya Dash. I am a PhD research scholar at NISER Bhubaneswar, India. So I am currently working under the group of Professor Subhankar Vedanta. So I will first like to thank the organizer for giving me an opportunity to present my research work here. So today I will be talking on my current research work, which focuses on the observation of inverse orbital Hall effect in chromium CFB heterostructures like okay, so coming to the introduction, as we know, spintronics uses the spin degrees of freedom of the electrons to manipulate and storage the data device and data storing devices, which major device is the magnetic random access memory, where basic storage unit is the MRAM, is the spin valves is basically a trilayer structure where a non-magnetic insulator is sandwiched between two ferromagnets. One of the ferromagnets has fixed magnetization, where the other the magnetization of the other ferromagnetic layer is free. So basically, depending upon the magnetization direction of the both the ferromagnets of a spin ball, we can get two resistive states, basically which say as the 0 1, which works as the 0 and 1 bit in the magnetic storage devices. So the most advanced type of the MRAM is the spin orbit torque based magnetic random access memory. So basically, this figure here. Mhm. So basically, this figure here is a schematic of the SOT-based MRAM devices. So where we control the free layer magnetization by the spin current. The spin current basically is when we inject this material below bar is basically a material having very strong spin orbit coupling. So when we apply a charge current through this material, due to spin dependent scattering, we get a transverse accumulation of the spin angular momentum in this direction. And this spin current, we call this as the spin current, and this spin current controls the magnetization of the free layer. So this is basically the schematic of the spin Hall effect, where when we inject a charge current, we get a transverse accumulation of the spins, and this generates a spin current, where the sigma is the spin polarization vector, which is orthogonal to the both spin current and the charge current densities. So, one of the major restriction in SOT-based MRAM devices is that we always need a material to have very strong SOC. So, but recently it has been seen that the low SOC materials such as 3D elements, 4D elements, transition elements can significantly has shown significant potential to control this free layers magnetization by using the orbital counterpart of the spin, that is by generating a orbital angular momentum or orbital current from the charge current. So this is basically a schematic of the orbital Hall effect, where we get a transverse accumulation of the orbital angular momentum to the current flow direction. So then how this orbital angular momentum generation occurs in a low SOC material? To take that uh, to explain that, I have taken a simple example from this famous Donguko's Professor Dr. Donguko's paper. Like if you the major factor that is responsible for the generation of this orbital Hall effect is basically the orbital texture, which is basically the interaction of the orbital wave function with the with the lattice. So this is a p orbit. This is the radial p orbital of a centrosymmetric crystal at equilibrium in the kz is equals to 0 plane. So if you take the expectation values of the orbital angular momentum, you will get the value 0. That means the orbital angular momentum is quenched, which is a basic theory of the crystal field theory was previously believed. But what happens when we apply an electric field? We alters the crystal momentum, and this in turn alters this orbital texture and generates a transverse orbital angular momentum. So this is basically the physics mechanism of this generation of the orbital Hall effect. But the electrical detection, but when you generate the orbital current, we cannot detect it electrically. So optically we can detect by different techniques, experimental techniques, but for electrical detection we uses the inverse phenomena, like that is the orbital pumping and by inverse orbital Hall effect, as one of the previous talk has already been discussed about this, so I am going briefly. So this orbital pumping is basically we take a bilayer of this ferromagnet and this low SOC material, and we inject this orbital angular momentum from the ferromagnet to this low SOC material, whereby inverse orbital Hall effect we detect the voltage. So this is basically the inverse equation, and this is the schematic of this inverse orbital Hall effect. So coming to the motivation, so this figure is basically describes the spin Hall conductivity and orbital Hall conductivity of different materials. So if you can see, the mostly SOT based devices has used platinum because it has a significantly high spin Hall conductivity. But recently it has seen that the 3D elements such as chromium, manganese, iron, these materials have shown the orbit has shown very high orbital Hall conductivity when exceeding the spin Hall conductivity of the platinum. So for that purpose, I have taken the chromium layer as my orbital sink, and the CFE I have taken the ferromagnet as my orbital source, because the CFE has very low Gilbert damping. But the only disadvantage is that the CFE does not possess a significant SOC, but the SOC. So we need a converter. We need a converter for the from the spin current to the orbital current to see this inverse orbital Hall pair. That's for that purpose I have taken platinum, a very thin layer 1.6 nanometer of the platinum in between the chromium and the CFB. So this is my sample structure. These upper two samples are basically reference samples, and this is the main sample where I have put the platinum below. And these samples have been prepared by sputtering techniques under ultra high vacuum environment. So we have done all the inverse orbital Hall effect from this setup, this experimental setup. So this is basically a waveguide. So we put the sample in a flip chip manner on this waveguide and apply a microwave signal through this waveguide and simultaneously sweep the external magnetic field simultaneously with so this is typically the FMR derivative spectra we observe from this experiment at different frequencies of the sample with chromium 10 nanometer, platinum and CFB. I have kept the platinum and CFB. This platinum thickness is kept constant at 1.6 nanometer and CFB at 9 nanometer, and all the samples have been capped with a 3 nanometer of silicon oxide. So these dark lines, like if you can see, so this dark line suggests the fitting of this FMR derivative spectra. And for the detection of the inverse orbital or inverse spin Hall effect, we have put a nanovoltmeter and we put the contact on the sample edge to detect the voltage. So this is the typical, this blue curve represents the FMR spectra of this chromium 10 nanometer sample, and this magenta curve is basically the inverse signal we detect from the nanovoltmeter. So this is basically a Lorentzian signal which can be fitted by this equation, which has both symmetric and antisymmetric part. The symmetric part majorly comes from this orbital and spin pumping, and this antisymmetric part comes from the rectification signals from the ferromagnet. So I measured the current by dividing the resistance of this, the set resistance of the sample. So okay. So coming to the FMR spectra, so if this is a basically plot between the resonance field versus the frequency of samples with different chromium thickness of the sample structure. So what I found, we feed this equation by this Kittel feed, and we extract the parameter gamma called as the gyromagnetic ratio, and then to calculate the alpha value, that is the Gilbert damping, we feed this equation, we plot the graph between the FMR line width versus frequency and feed by this equation. So the summary of this analysis is that with different chromium thickness, we can see the M effective value of the sample is not changing. That shows a consistent growth of the CFB on different chromium thicknesses. And this red value shows the Gilbert damping factor, and this is not significantly changing with the chromium thickness. And this is a clearly signature also of the orbital pumping or orbital torque. So this curve is basically we have extracted only the symmetric part from the measured ISHE or ISHE and IOHE signal of the chromium 10 nanometer sample of the sample. So when you alter the magnetic field direction by 180 degree, we see the signal polarity is also reversing. That is a clear signature that this the signal what we are observing is basically due to the spin orbital pumping. And this is a systematic variation, like when we vary the chromium thickness, what happens to the measure current or measure signal. So what we observe is that with increasing the thickness of the chromium, we are clearly seeing an enhancement in the measured signal of from the nanovoltmeter. So this clearly, and also the polarity of the symbols is positive. That clearly signifies this positive polarity means the positive orbital Hall conductivity of the chromium and the positive spin Hall conductivity of the platinum is getting added up. So this is clearly enhancing the total signal from the nanovoltmeter. So this is basically the plot where till the 10 nanometer sample we see the symmetric value of this signal is increasing. But what we observe, there is a ambiguity at the there is a difference at the 50 nanometer of the chromium sample, but we observe a decrease. But this phenomena of decreasing we are currently looking like, we speculate that this decrease might be due to the negative spinel conductivity of the chromium at higher thickness, which is dominating. For that speculation, the chromium diffusion length should be the chromium spin diffusion length should be high enough. So previous some reports are there that project this long spin diffusion length in chromium. So that might be a region, but we for now we have not sure that why there is a decrease for this. So then we do the power dependency spectra of the measured signal of this chromium sample, or chromium 10 nanometer sample. So what we observe at lower power regime, we see a linear enhancement of the measured signal, which so again confirms the signal is basically due to a inverse orbital spin orbital Hall effect. And this nonlinearity at the higher power is basically due to the thermal effects, and this spectra is basically the seat resistance which we calculate from the Van der Pau technique for different samples with different chromium thickness. What we observe clearly decrease with the chromium thickness. So this plot is basically the plot of the some standard reference sample which I have shown initially. The black curve is basically only CFP layer, where we see a very low measured signal, very low measured signal from the nanovoltmeter, and also a very strong asymmetric value, antisymmetric value, which shows the spin pumping and orbital pumping self-induced thing is very low here, and majorly the rectification contribution is there. But this magenta curve is basically chromium and CFE. So basically we see a very small change in the signal, but when we put a plus 1.6 nanometer of platinum between this chromium and CFE, we see a very strong, almost six-fold enhancement of this of the measured signal. So this is basically the Gilbert damping of the different samples. So we see a enhancement in the Gilbert damping when we put a platinum of 1.6 nanometer. This is obvious because this spin relaxation when occurs, this enhances the Gilbert damping factor. So on summary, I will say that this and putting by putting a very small thickness of platinum significantly enhances the measured signal, and the polarity of the signal is positive, which signifies this platinum's inverse spin Hall effect. And that when the spin angular momentum gets pumped from the ferromagnet to the platinum, its small amount of it is converted to inverse spin Hall effect voltage, and the other is getting propagated on, and the rest is getting converted into the orbital current and getting injected into the chromium, where it is getting converted to charge voltage by inverse orbital Hall effect, and these are getting added up. So finally, I would like to thank my supervisor and the group members for their constant support and guidance. So thank you.
Thanks for your nice talk. And now the Q&A question. We have one from the chat that you have related the decrease with the negative spin Hall conductivity at higher thickness, at which the decrease, but considering the diffusion length of chromium close to 7 nanometer, should it not decrease?
Yeah. Yeah, that value is quite. We are not sure, but why we have seen a decreasing value. So we speculate that might be due to this negative chromium thickness, negative chromium spinel conductivity. But for that, the chromium spin diffusion level should be large enough. So basically, I am not sure about this result. So so we are like looking into it. So.
Okay, thank you. So, is there any other question? Kathleen? Okay. If no other question, we will let's thanks the presenter again, and we will welcome next speaker,